Hey guys, this is Tensor. Welcome back to the Golang blockchain tutorial. This is part 3 of this series. Today we're going to be adding a command line interface and persistence to our blockchain. Currently, if we want to add blocks to our blockchain, we have to actually hard code them inside of the main function like this. Also, we have no ability to save a blockchain after we run the application. And so every single time we add a new block, we have to just rerun the application, which runs through the entire blockchain again. Now this is no good, especially if we want to be able to share our blockchain or even add a network to our blockchain. The way that we're going to deal with this, though, is by creating a persistence layer which uses a key value store database. Now it's worth noting that in the original Bitcoin paper, there's really no specification for the type of database that you can use. So when you're building a blockchain, you can really use any kind of database that you feel fits the use case. Bitcoin itself and a lot of the other cryptocurrencies use a database called LevelDB, and this is a pretty low-level key value storage database. The database that we will be using in this application is called BadgerDB, which is a native Golang database, which is also a key value storage database that is based off of LevelDB. This means that there are no tables like SQL, there's no query language, there are no columns or rows. We just store everything by creating byte keys and byte values and putting them directly into a bunch of files which go into a folder. Let's get into this by adding a new file to our blockchain folder called blockchain.go. And inside of this file, we want to move all of the stuff that's connected to the actual blockchain struct. So essentially, we just want to move the struct itself, the init blockchain function, and the add block function. Now, because BadgerDB only accepts arrays of bytes or slices of bytes, we need some way of serializing and deserializing our block data structure into bytes. So back inside of the block.go file, we'll create a serialize and deserialize function for our block structure. Let's start with the serialize method. So this is a method on the block struct, and it outputs a slice of byte. We create a result, which is a bytes buffer. And then we're going to use a library called encoding_gob to create an encoder on our results bytes buffer. We can then call encode on the block itself using the encoder that we created up here. And this function passes back an error, so we need to do some error handling. And after we run the encode function, we can just return the bytes portion of our result, which will just give us a byte representation of our block. Now let's create the deserialize function, which takes in a bunch of data in the form of a slice of byte and outputs a pointer to a block. Like we did with the serialize function, we can create a decoder using the gob library. This time though, we're going to pass in bytes new reader with the data inside of it. This creates a bytes reader, which then gets passed to the new decoder. Then we can run decoder decode on our block, and this will pass back an error which we want to handle, and then we'll return a reference to the block which we created inside of this function. And actually, while we're at it, let's create a handle function so that we can properly handle all of the errors that we're going to have to deal with. So in both deserialize and serialize, we can now just call handle with error inside of it, and it will handle our error properly. Now that we've created these utility functions, we need to consider how we want to store our blockchain data. In the Bitcoin core specification, there are two main groups of data. You have the blocks, which are stored with metadata, which describes all of the blocks on the chain. And then you have the chain state object, which stores the state of a chain and all of the current unspent transaction outputs, as well as a few pieces of metadata. With Bitcoin, each block has its own separate file on the disk, and this is done mainly to increase performance. Essentially, by splitting each block into its own separate file, we don't have to open up multiple blocks if we want to just read one hash or one block. Now, this is something that we won't be implementing in this blockchain, but it shouldn't be a big deal because we won't have a large blockchain in this application. Let's go ahead and refactor our blockchain struct with our Badger database in mind. So I've imported Badger, which is at github.com/dgraph-io/badger, and now the blockchain struct, rather than just being an array of blocks in memory, it will store the last hash, which is the last hash of the last block in the chain, and then it will store a pointer to our Badger database. Also, while we're at it, we can go ahead and create a path to our database. And this will be in a folder called tmp/blocks, which we want to also create on the disk. Now notice after we change our blockchain struct, the init blockchain function and the add block function both have a bunch of errors in them now. This is fine, of course, because we're going to rewrite both functions to actually put our blockchain into our database. Let's start with the init blockchain function. We want to open up our database. So we're going to first start dealing with the Badger default options. And with this options struct, we want to specify where we want our database files to be stored. So we can set up this ops dir path and then the ops value dir path, and we can point both of them towards the same path. The dir part of the options struct is where the database will store our keys and our metadata, and then the value dir path is where the database will store all of the values. Of course, this doesn't matter because we're putting them both in the same folder. Once we've created this options struct, we can go ahead and open up the database by calling badger.open. And this returns a tuple with a pointer to the database and an error, which we can handle with our handle function. We can access the Badger database using one of two functions. We have an update function which allows us to do read and write transactions on our database, and then we have a view function which allows us to do read-only transactions on our database. Now, because we're initializing the blockchain and because we're essentially just going to be putting the Genesis block and the actual blockchain itself into the database, we need to have write capabilities, and that's why we're going to use database.update. Also notice that in this update function, we're passing in a closure which takes in a pointer to a Badger transaction and passes back an error. Inside of this closure, we have access to the transaction and we can use it to do things to our database. There are really four main pieces to this entire initialize blockchain function. So we've already opened our database. Inside of the DB update function, we want to check to see if the blockchain has already been stored in the database or not. If there is a blockchain there, then we'll create a new blockchain instance in memory, and we'll get the last hash of our blockchain in the disk database and push it into this instance in memory. Now, the reason why the last hash is important is because that's how we can derive a new block in our blockchain. Now, if there is no existing blockchain in our database, we'll create our Genesis block, we'll store that in the database, then we'll save the Genesis block's hash as the last block hash in our database, and then we'll create a new blockchain instance with the last hash pointing towards the Genesis block. So first we can verify whether or not we have a database or a blockchain in our database simply by running if transaction get. We pass in the key LH, which stands for last hash, as a byte. If this comes back with an error, meaning it doesn't exist, and the error is Badger error key not found, then we know we don't have a database inside of our application. And this also means that we don't have a blockchain in the database. So now we can go about creating our Genesis block and proving it, and then we can use the Genesis hash as the key for the Genesis block, and we can serialize the Genesis block itself and put it into our database using the transaction set function. Then, as mentioned before, because our Genesis block is the only block that we have in our database, we want to set its hash as the last hash in our database. So we'll set it to the key of LH. And we also want to take our Genesis block's hash and set it to our last hash variable so that we can put it into our memory storage. Let's add a little bit of error handling here as well. So for this error, we have to call our handle function. And then for this error, we can pass it back from the closure and then handle it outside of the DB update function. Now, as I mentioned before, if we already have a database, and if that database already has a blockchain inside of it, we want to do some other things. Namely, we want to get the last hash from that database, and we can do this by calling transaction get on the key that we stored the item at, which is the LH key. This will give us a pointer to an item struct and an error, and then we can then call item.value to get the value from the item struct, and we can put that into our last hash variable. And this function also passes back a tuple as well. And finally, we can return the second error if it does indeed happen. And in between, we can handle the first error. Now, outside of the DB update function, we want to handle the error that was passed back from it, if there is one. Then we'll create our new blockchain in memory, which will contain the last hash variable and a pointer to the Badger database. And finally, we'll return a reference to this blockchain so that we can use it further inside of our application. We also need to refactor the add block method. So first we need to execute a read-only type of transaction on our Badger database. So we can call the database from our blockchain by calling on chain database and then calling view to get a read-only type of transaction. And again, this takes in a closure with a pointer to a Badger transaction, which returns an error. This part is actually pretty simple. We just want to get the current last hash out of the database, which is of course the hash of the last block in our database. And once we call transaction get, we'll get our item, and then we can unwrap the value from that item and put it into our last hash variable from up here. And we can return an error if we do have one, and of course handle the first error if we have one of those as well. And then we'll take the last hash that we got from this database view function and create a new block with the last hash and the data that we're passing into the add block function. With our new block now created, we now want to do a read-write type of transaction on our database so that we can put the new block into the database and then assign the new block's hash to our last hash key. So as we did with our Genesis block, we can use the block's hash as the key, and then we can serialize the new block itself and put that in as the value. And we can do this with the transaction set function. Then we want to handle an error if we get one. Then, as I mentioned before, we want to set the new block's hash as our last hash value so that we can easily get it out of our database and derive a new block if we want to make one. And then finally, we want to grab our blockchain and grab the last hash field and set it equal to our new block's hash. And that's actually all we really need to do for the add block function. So this is cool and all, and we've successfully created a layer of persistence for our blockchain. However, we've lost the ability to go through our blockchain and print it out like we had it before. So before, when we ran our application, it would run the proof of work algorithm, print out all of the hashes, and then it would run back through all of the blocks and show us the blocks, the data, the last hash, and all that other stuff. Now, because all of our blocks are inside of the data layer, we can't actually just do that. To reclaim this feature, we're going to create another structure, this time called blockchain iterator. And this will be a structure which we can use to iterate through our blockchain, which is in the database. This structure has two fields. It has a current hash field, which is sort of like the last hash field, and then it has the database field, which again is a pointer to our Badger database. Now, Badger has some really nice iteration functions, but let's implement this manually so we can kind of look at how an iterator would be implemented for a blockchain like this. So first we want to be able to take our blockchain struct and convert it into a blockchain iterator struct. And we can do this simply by passing in the chain last hash and then the chain database, for the blockchain iterator's current hash and then the blockchain iterator's database. It's important to note that because we start with the last hash of our blockchain, we're actually going to be iterating backwards through the blocks. So when we iterate through our blockchain, we'll iterate from the newest all the way to the genesis block. So now, after being able to convert our blockchain into a blockchain iterator, we need to create a next function which we can call on the blockchain iterator to iterate through our blockchain. And this will return a pointer to a block. When you create an iterator in almost any programming language, the way it works is by calling the next function until it hits the end of the data structure. For our next function, we need to read from the database, so we can call iter database view, and this will be a read-only transaction. Inside of our closure, we can call transaction get on the current hash inside of our iterator. This will give us back a tuple of an item and an error. We can then call item.value to get a byte representation of our block as well as an error back. And then we can use our deserialize function on the encoded block to create a new block in the form of our block struct. And finally, if we have an error from this last function, we can return it from our closure. And we also want to handle any potential errors that get passed back from our iter database view function. After deserializing the block into our variable, we want to then change the iterator current hash to the block's previous hash. So remember that our blocks each point to their previous block in the blockchain using this previous hash value. And so we can use this structure to be able to fetch the next block out of our database and just keep going backwards through the blockchain. And that's all we really need to do for our iterator. Now let's create a command line interface which will allow a user to pass in a new block and also print out the blockchain. Inside of our main.go file, we can create a new structure called command line. And inside of this, we'll have our blockchain, which will just be a pointer to our blockchain struct. Let's add some instructions for the user. So here we'll create a method called printUsage, which will print out that the usage for our command line is to call add-block followed by the block data in the form of a string, which will then add a block to the chain. And then if the user calls print, then it will print out the blocks in our blockchain. We'll need another method called validateArguments, which will allow us to validate any arguments that we passed through the command line. So these are arguments that come after the main call. So we want to check to see that the length of our operating system arguments is less than 2. And if it is less than 2, then we'll just print out the usage because the user hasn't entered in a command. And then we're going to call runtime.goExit. And this is actually an important call because what it does is it exits the application. But unlike os.exit, it exits the application by shutting down the go routine. One of the small downsides to the Badger database is that it needs to properly garbage collect the values and keys before it shuts down. So if our application shuts down without properly closing the database, it can potentially corrupt the data. So we can use this runtime.goExit command to initiate a shutdown. Now let's add a method to our command line called addBlock. This will call to the blockchain inside of our command line interface, and then call the addBlock method on the data which is being passed in from the command line, and then it'll just print out that we've added a new block. The other command that we have is to print out our blockchain. And this method is pretty easy because all we need to do is grab all of these print statements and put it into this print chain and use our iterator to iterate through our database. So first we can access our iterator by calling CLI blockchain.iterator, which converts the blockchain struct into an iterator struct. Then we can create a for loop, and inside of here we can add our print statements. So we can say our block is equal to iter.next, which is the method that we created. Then we can cut out our print statements, and paste them up here. So we have our print statement for the previous hash, the print statement for the data, the print statement for the main hash of the block. And then we want to run our proof of work on the block to prove the block. Then we'll run the proof of work print statement, which prints out either true or false. And then we'll add another line between each of the printouts so that we can actually properly read it. We can break out of this for loop if the length of the block's previous hash is equal to 0. So when we get back to the Genesis block, it doesn't have a previous hash, and therefore its length will be 0. Now finally, we want to create one last method for our command line struct, and this one is just called run. Inside of this run method, we can just call all of the other methods that we created. So first let's run the validate_args method. Then we can create some flags for our command line tool to operate. So if the user types in the string add after they execute the program, we create a new flag set. If the user types in the string print afterwards, we can do the same thing. And then we can also add a subset to our add block command, which will say, okay, well, if the user types in add, and then if they type in -block, then they can type in the block data as a string. Now let's get the arguments that we pass through the command line by calling a switch statement on os_args, and we're going to call it on the first argument after the original call to the program. In the case of the string add, we want to add a block to our blockchain, and we can do this by calling on our add block command, and then we can call parse on it, and we can parse all of the arguments which come after the first argument in our argument list. Then we can handle the error, and we can do this by calling to our blockchain library and calling the handle method that we created from before. Now let's go ahead and add the case for the print string. So if the user types in the print string for the first arg of the arguments list, then we want to call to our print chain command and then parse all the arguments after the first argument of the list. And then finally, we can put in a default case. So if the user types anything else, or if they type nothing, then we'll just call CLI print usage, and then we'll execute the runtime go exit command to gracefully shut down the go channel and then the program. Now when we parse these flags, if they don't throw back an error, they give us a Boolean value of true, which we can check by calling the parsed method on the flag. So we can say if add block command has been parsed, then do something, and we can do the same for print chain command. So with add block command, we want to check to see if it's parsed. Then we want to check to see if a pointer to the add block data string is an empty string. If it is an empty string, then we'll just print out the add block command usage, and then we'll execute a go exit from our application. If it's not empty, then we can take the data inside of the add block data and make a new block in our blockchain. For our print chain command, we just want to check to see if it's parsed, and if it has been parsed, we can just run the print chain method on our command line interface. And that's all we really need to do to add the command line interface to our application for now. Now let's just fix up our main function. There are a few things that we just want to do in the main function. So we're already creating our blockchain by calling init blockchain. Now because init blockchain is opening up the database, we want to call defer chain database close to properly close the database before the main function ends. Now this defer command only executes if the go channel is able to exit properly, and that's why we're using these runtime go exits rather than OS exit commands. Another way to ensure that this properly happens is to add a line to the top of the main function with defer os.exit 0. So again, these are all just fail-safes to help us properly close the database and give it time to garbage collect the keys and the values. Now finally, we want to create the command line interface struct by passing in our blockchain, and then we just want to call the run function. Now before I go ahead and show you guys the application in action, I just want to note a few things. If you go into your Go mod file, you'll notice that there's now this big require block because we imported the Badger library, and so it also imports all of the other dependencies that Badger needs. And you can see that these ones are flagged as indirect because they're just dependencies of Badger rather than dependencies of our application. Also, we have the go_sum file, which I mentioned before is like a yarn lock or a package lock file. Now, even if you don't have the require block inside of your Go mod file, when you go ahead and run the application, it will go and try to find the dependencies on your computer, and if they're not there, it'll go ahead and download them. So here you can see I'm running go run main.go, and I'm running it with the arg of print, and you can see it says finding the dependencies, and then it goes ahead and tells us that we have no existing blockchain. It proves the Genesis block, and then it prints out our current blockchain, which is just the Genesis block in this case. Let's add a new block to our blockchain. We can do this simply by running go run main.go add -block and then a string for the actual data inside of the block. As you can see, it runs through the proof of work algorithm, and we also get this printed out information because we're using our Badger database. Once it proves the block, it prints out added block and then it just exits. We can go ahead and print our blockchain again. And you can see it actually executes a lot faster because it doesn't need to prove any of the blocks, it just needs to get them out of our database. So we've got our first block and then we've got our Genesis block. Let's add another block. This time we'll add the data that says send 10 BTC to Jackie. Again, it goes ahead and tries to prove the hash, so it needs to find the hash that meets the difficulty. And once it finds the hash, again it prints out added block. And we can go ahead and print out our blockchain again. This time we have 3 blocks. Now there is one more thing to note. If we come in here and change the difficulty, say let's lower it to 12, and then we go ahead and print out our blockchain, you'll notice that the proof of work part of our printout will come back as false. Now the main reason for this is because we're only storing the nonce of our block inside of the database, not the actual validation boolean. This means that when we go to print it out, the actual hash has not been signed for the new difficulty, and so when we run the validate function on the nonce which is stored in the blockchain, it comes back as a failure. So as this application is currently, we can't have a dynamic difficulty for our proof of work algorithm. If we wanted to have a dynamic difficulty, then we would need some way of basically replaying through the blockchain so that we could re-sign the blocks to the new difficulty. And this is something that we'll think about adding in the future. Alright guys, well I hope you enjoyed this video. If you did, feel free to like and subscribe. If you have any questions or comments, feel free to leave them in the box below. And if you disliked this video, then by all means downvote it as much as you like. Have a good night.